I'll just call off when it's live. I think we are live, guys.
Alright, I'd like to start by thanking our sponsor Infogain for facilitating today. Infogain is doing path-breaking work in making it possible for brands to design products based on customer input and then sell them globally at unprecedented scales. A very good evening to all of you who are attending. I thank you all for joining us on this eventful night. When it was first invented, the Internet was welcomed as an instrument for equity and positive social change. In the past, the Internet was merely a fascinating gizmo that seemed to hold the answers to all questions in life. Over time, the Internet has evolved from being a tool used by humans to becoming a tool that might challenge humans. We have always been on the lookout for the moment when technology would cross the singularity. It would overwhelm our strengths or replace our jobs or perhaps become more intelligent than us. However, much before that moment, there comes the all important moment where it begins to surpass human weaknesses. And it is at that watershed point that we stand today. As we stand at the threshold to the future, asking ourselves exactly where we want to take this beautiful thing called the internet, it is an honor for me to introduce Mr. Vint. The topic for today's talk is the era of the internet, the past, the present, and the future. And who better to deliver this talk than the man who is widely regarded as the father of the internet? While working as an assistant professor, he laid down the foundation of the internet's architecture by specifying a protocol for the transmission of data packets. From leading the efforts at building the first commercial mailing service at MCI to working with NASA JPL to build an interplanetary internet, Mr. Cerf has built quite a reputation of being an innovator. He has held a plethora of prominent positions, including the VP and the Chief Internet Evangelist of Google, President of the ACM, and has also served on the National Science Board. The many feathers that Turn has had include being awarded the prestigious Presidential Medal of Freedom, National Medal of Technology, as well as the prestigious Turing Award. Separated by miles and connected by, well, the internet, it is my pleasure to present you the final speaker in the Think Again series of Apogee 2021, Mr. Vint.
Thank you so much for letting me join you today. I thought we would go through sort of the history of the internet and some of the lessons that I've learned as a result. One of them is don't get too cocky. So let's start out. First of all, it's not easy to predict the future, and so I certainly would not have predicted everything that's happened in the internet, but I thought you'd like some examples of other people who haven't succeeded in making very good predictions. Here's one from Western Union in 1876. They didn't think much of the telephone invention of Alexander Graham Bell. Remember, they were doing telegraph communications. Too many shortcomings to be seriously considered as a means of communication. The device is inherently of no value to us. So much for that decision. Clearly, AT&T emerged as a giant in later years. Here's another example. I can't believe this one. In 1899, the commissioner of the U.S. Patent Office said everything that can be invented has already been invented, and he was proposing to shut down the patent office. Several million inventions later. Here's another one. I love this one. I've traveled the length and breadth of the country and talked with the best people, and I can assure you that data processing is a fad. It won't last out the year. This is the guy who's in charge of business books for Prentice Hall, the major publisher. If you're getting a sense for what's going on, this is my favorite theorem, 206. Everything is more complicated. And I bet that you, like me, have discovered that as you look more deeply into anything, it gets more and more complicated. And so you should be prepared for that. This is taking you back over 50 years ago now to see what the original Arpanet looked like. This was the first wide area experiment with packet switching technology. I was a graduate student at the time at UCLA, and I worked on the software of the Sigma 7 computer down there in the bottom to connect it to the first packet switch, which we called interface message processors, or IMPs. So there were 4 of them in the original network, and the idea was to use this particular setup in order to test the idea of packet switching to allow computers of different brands and different operating systems, different word sizes, all kinds of different characteristics to interact with each other in a smooth way. And so we succeeded in getting the intercomputer communication protocols to work. But This only worked on one single homogeneous network. Now, this network itself actually grew fairly rapidly to not only to cover a significant part of the United States, but also extended into Europe as well. It was a platform for research to link computer science departments together and military organizations together in order to make use of computers. But my partner, Robert Kahn, and I learned that the success of this experiment led the Defense Department to pursue an interest in the use of computers for command and control. Could I use a computer to manage my systems, my assets better and more effectively? And if I could, then a smaller force, for example, might actually overcome a bigger one because of the better management of resources. So we call this a force multiplier. So that led to the next thing, which, I should tell you, this is, sorry, let's get this. This was just a funny opportunity. In 1994, my colleagues and I wanted to help Newsweek magazine celebrate the 25th anniversary of the Arpanet. We spent the entire day getting green zucchinis and yellow squash and some plastic yellow cord and 5-pound tins of coffee. And we and the background that you see, we spent the whole day setting this shot up. To show people how primitive the Arpanet was when it was first built, and if you look carefully, you'll see that there was a geek joke embedded in this, because you'll see that the coffee tins go ear to ear and mouth to mouth, but nobody goes mouth to ear. So this network would never have worked. So that was our contribution to geek humor on the 25th anniversary of the Arpanet. The internet idea was introduced by my colleague, Robert Kahn, who had worked on Arpanet for a company called Bolt, Beranek, and Newman, and then had gone to the Defense Department to join the Advanced Research Projects Agency in 1972. In 1973, in the spring, he came out to my laboratory at Stanford and said that the Defense Department wanted to consider the possibility of using computers in command and control, but he pointed out that in order for that to work, you would have to have computers in ships at sea, in aircraft, and in mobile vehicles. The Arpanet was built on dedicated telephone circuits connecting the packet switches to each other, and you couldn't use dedicated telephone lines to hook up the airplanes and the ships at sea. So he started work on a mobile radio network, which eventually was put into test operation in the San Francisco Bay Area, and also a packet satellite network with multiple ground stations sharing a common satellite channel using Intelsat 4A. So by the time he and I had gotten the internet specifications more or less laid out, which would be in December of 74, the first TCP spec was completed by me and some of my graduate students. We started implementing in 1975. By 1977, this configuration was available to us. And I had moved from Stanford to the Defense Department, to the Advanced Research Projects Agency to manage this program. So it was very important to me as a program manager to demonstrate that this TCP/IP protocol system would actually allow these different kinds of packet switch nets to interact smoothly with each other. So we had a big van over on the left side of this screen driving up and down the Bayshore Freeway, radiating packets, which went through a gateway. Today you'd call that a router, but we didn't know that, so we called it a gateway. Through the gateway into the Arpanet, then all the way across through an internal satellite hop to Norway, and then down to London, to University College London, where another TCP/IP implementation was being done. And then into another gateway, into the satellite network, and then back across the Atlantic to the United States East Coast, and then back across the Arpanet again to Los Angeles at USC Information Sciences Institute. So some of you will know that Los Angeles and San Francisco are about 400 miles apart. So that's really, the effective path of the packets. But the actual path was through two synchronous satellite hops back and forth across the Atlantic in the United States twice. And it worked. And I remember, leaping around in the office thinking, this is a miracle. You all understand that packet switching is software, basically. And when software works, it's a miracle. So this was the first real demonstration that TCP/IP could actually handle a multi-network environment with very, very different packet switch networks, different data rates, different latencies, different error rates, different packet formats, different address structures, and to make it look all uniform. So in the mid-1980s, early and mid-1980s, the National Science Foundation saw the success of the Arpanet and the Internet and decided that it wanted to build a backbone network which could connect about 3,000 universities around the United States. And so it began to build a backbone network that it called NSFNet for National Science Foundation. Then it built or funded another dozen intermediate networks that would then connect to the universities. So the idea was to have the backbone connecting the intermediate nets and the intermediate nets connecting the universities. So this all took place during a period from about 1986 to 1995. In that same time frame, the Department of Energy decided that it wanted to use the same TCP/IP technology to build a network linking its laboratories together with access to supercomputing resources. So they built the Energy Sciences Network. And NASA, which also has a collection of laboratories, wanted also to connect them together. And they again used the TCP/IP protocol and built their own NASA Science Internet. So we had Arpanet, NSFNet, NASA Science Internet, and the ESNet in the United States by the mid to late 1980s. And in that same general time frame, we started to see other research and education networks popping up in Europe, in particular in Northern Europe, Norginet, for example, in Japan and elsewhere. So this was a very important step in the expansion of Internet and the demonstration that it was capable of scaling up to much larger sizes. This is what the Internet looks like. Some of you actually may have seen this before. It's actually an older picture of the Border Gateway Protocol routing tables. It's showing how many different networks there are. We call them autonomous systems for good reason, because they're operated independently of each other. Each of the operators picks what it wants, what software it wants. It decides who it will connect to and on what terms and conditions. There's no central control here at all. It's an entirely distributed system. And it works, of course, because they've all adopted the same standard. The only centralized element of all of this is the management of domain names and of internet address allocation. Those two have to be done uniquely so that you don't have two people assigned to the same internet address, parties owning a domain name. And that task, that coordination task, is done by the Internet Corporation for Assigned Names and Numbers. It's a nonprofit based in California, but it's an international organization. So all of this works because of coordination and collaboration on a global scale. I suspect that every one of you already knows how the Internet works, so I'm not going to belabor this slide, but I will tell you, some people ask, and I've found a very convenient analogy, metaphor, if you like. If you think about postcards for a minute, everything you know about a postcard applies to an internet packet. You put a postcard into the post box, and there's some probability that it will come out on the other side to wherever it is that you intended it to go. But there's also a probability that it won't. So the post office is what I will call a best effort system, and so is the internet. There's no guarantee when you put an internet packet into the system that it will come out the other end. Most of the time it does, but sometimes it doesn't. Also, if you put two postcards in the post box aimed at the same destination, they don't necessarily come out in the same order you put them in. That's also true in the internet. The internet actually does something the post office doesn't do. Sometimes you put one internet packet into the internet and two of them come out because of alternate routing. You may actually transmit the internet packet twice. And as far as I know, the post office doesn't offer that as a service. In order to discipline this somewhat unruly basic internet postcard layer, and put another layer on top of it we call the transmission control protocol. And the way that works, in very simple terms, is morally equivalent of what would happen if you were trying to send a book to your friend and you only had postcards to do it with. You'd have to tear the pages up, cut the pages up, paste them onto the postcard, and then you'd notice that not every postcard had a page number because you cut the pages up, but you know that they could get out of order. So you number every postcard, 1, 2, 3, 4, 5. Then you keep copies because you know that some postcards will be lost. And then you start sending postcards to your friend. And then you wonder, how do I know if I should start sending duplicates? And then you get this brilliant idea, I'll have my friend send me a postcard that says, hey, I got everything up to postcard number 420, so you can throw those copies. And then you realize that your friend's postcard could get lost. And so now what do? And say, well, you look at your watch and you say, well, have I heard anything back from my friend? After a certain amount of time, I'm going to start sending duplicates until I do get a postcard saying I got everything up to 420. That's basically how the TCP protocol works. Oh, except for one other thing. Imagine that the book that you're sending has 1,000 pages and it turns into 2,000 postcards. And you take it to the post office and you give them all 2,000 postcards. And by some incredible miracle, all 2,000 get delivered to your friend on the same day and they don't fit in his post box. So some of them fall on the ground and get blown away by the wind. And so you have a deal with your friend. You won't send more than, say, 200 postcards at a time until you get a confirmation back so you don't overload the post box. That's called flow control. Now you know how the internet works. So that's how I try to explain to people in simple terms what's actually going on in those two very important layers of the internet protocol. Now, cloud computing, I just want to mention to you that this is in some ways not new, and in some ways it's very new. Cloud computing has arisen as a reincarnation of time sharing. Time sharing got started in the 1960s when it was possible to build machines that ran fast enough that more than one person could use it at the same time, feeling as if they had total control over the machine, even though it was simply sharing its assets very, very quickly. Cloud computing is kind of like time sharing on steroids. And we build this gigantic building. It's full of computers. Some people call it warehouse computing. And in some people, the idea is that we simply replicated the concept of time sharing on this gigantic scale. At Google, we have a large number of data centers scattered around the world, all interconnected by extremely high-speed optical fiber networks. And so one of the things that I had been curious about is whether we would see a reincarnation of the concept of internet in the context of cloud computing, because I'm sure many of you know that there are several different cloud computing providers. Google is one, but so is Microsoft, so is Amazon and IBM and others. And so I've been thinking that the same thing that drove the internet to interconnect different kinds of packet switch nets would drive the interconnection of the cloud computing systems. And so we may end up with some intercloud communication protocol. And in fact, there is one. It's called Anthos, which is a product that we offer at Google that allows cloud computing systems to interact with each other. In particular, you can send containers, we call them Kubernetes, which is a Greek term, in order to allow the same programs to run on more than one cloud. And so we have a kind of growing intercloud capability as time goes on. And one of the reasons that someone might want to actually run programs on more than one cloud is that some clouds might have special capabilities. We have, in addition to regular CPUs, we have graphical processing units, we have tensor flow processing units, and someday we might have quantum processing units because we're working very hard on quantum computing at Google. And the other cloud vendors similarly have interesting resources that users might want to take advantage of. Since we only have a finite amount of time, I'm not going to dive very deeply into security here, but I want to point out to you how vital it has become and how poorly it has been addressed. You see headlines all the time of internet being interfered with, and people's machines being invaded, or their personal information being exposed, or banking account data being used to drain the account. Fraud and all kinds of other abuses have happened. And I will come back to that in a bit. But many of us have been introducing a lot of cryptographically aided mechanisms in order to defend against some of these bad behaviors. So the Hypertext Transport Protocol, which supports the World Wide Web, which was introduced by Tim Berners-Lee in 1991, now has a security layer. It's called TLS. And more recently, Google introduced something called QUIC, which combines the TCP protocol with the underlying TLS protocol to make it more robust and more manageable from the flow control point of view. And of course, at the internet protocol layer, the postcard layer, if you like, we have IPsec, which is end-to-end cryptography. All of this is taking advantage of public key crypto, which was developed in the mid-1970s by some of my colleagues at Stanford University and has evolved over time. We use it for the domain name system security mechanism to sign the entries in the domain name system so people can't fake the binding between domain names and internet addresses. We have what's called routing PKI, public key infrastructure, in order to digitally sign the border gateway protocol announcements to tell us how the internet is interconnected and to serve to route packets through the system. You don't want people to announce fake connectivity and then try to pull traffic where it doesn't belong. And so this is a way of making sure that the routing updates are legitimate. Two-factor authentication, I'm sure many of you are familiar with, can use strong authentication mechanisms, public key cryptography, in order to strengthen the way you identify yourself beyond simply a username and a password. So we have many things going on at Google in our cloud computing environment intended to address a great many of these things. I'm going to skip over open source, except to say that it's become an extremely important aspect of online computing. If you're trying to build new products and services, having the ability to get software from an open library can be very enabling. There is an issue, however, because since everybody has access to open source, there's an assumption being made that all the bugs have been found because it's visible software. And the answer is, since everybody is in charge, nobody's in charge, and a lot of that software actually has bugs in it. So if you're thinking about using open source libraries to build a product or a service, please scrutinize the software very carefully, because it may or may not be safe to use. There are all kinds of things that I'll call unfinished business, and this is where we get into some of the issues I raised a little earlier. One thing which I'm sure all of you must be conscious of is that an increasingly large number of devices are now coming equipped with internet access or internet capability. Some people call it the Internet of Things. Some people call it cyber physical systems. I did an inventory just recently around the house and discovered I have over 40 devices that are internet capable in the house. Some of them are just sensors for temperature, humidity, light levels, and things like that, just to monitor the heating, ventilation, and air conditioning. Some of them are access control security mechanisms. Some of them are just appliances. A lot of them are laptops, desktops, pads, mobiles, and things of that kind. It's amazing how quickly this adds up. So we see this rapid proliferation of devices with software in them. And apropos of my earlier comment, a lot of that software is taken from open source libraries because people are not charging a lot for some of these devices. Some of them are only tens of dollars, and so they can't afford to spend a huge amount of time doing all the development. The result is a lot of open source software in the IoT space, which means a lot of risk potentially. Another thing, and you can see here on the slide, reliability, safety, privacy, security, interoperability, and autonomy. These are aspects, or how shall I say it, features of IoT devices that I think you would want. You want them to be reliable. Why would you want a light switch that only works 80% of the time? You want them to be safe. You certainly don't want an internet-enabled microwave to blow up. You want them to be private. So if you have webcams around the house, you don't want other people who don't have your permission to go look at you or your house through the webcams. If you're using these for security purposes, you need for them to be impenetrable. You need to be able to buy devices from multiple vendors and have them interoperate in the same way that the internet allowed computers from different vendors to interoperate. And finally, autonomy is important here. And by this, I simply mean that if you suppose you had a house full of all these devices, and one day your internet connection stopped, you don't want the house to suddenly stop working. Like the refrigerator won't open and the toilets don't flush and whatever else it is you're relying on. So you need these devices to be able to run even if the internet isn't there, even if you might not be able to configure them until the internet comes back up again. This middle topic, though, the one misinformation, disinformation, and critical thinking, is probably the central topic of today's internet, and it has to do with the rapid spread of misinformation and disinformation, especially in social media. And so figuring out how to counter the presence of that kind of information is a serious conundrum, and I would say that we are still far from being able to solve it. Some people wave their hands and hope that machine learning and artificial intelligence will somehow allow us to filter out bad information, but I can tell you that that's probably an unlikely scenario because it's so difficult to figure out what is disinformation and misinformation. A classic example is to present someone with a bunch of statements, some of which are false, but which mislead you into thinking in certain terms. The trouble is, if you mix together statements that you know to be true, you may be inclined to believe, well, if this is true, then the rest of them must be true too. Why would somebody mix those together? Well, the answer is they want you to misunderstand things. So this is a serious problem. Some people have said that the misinformation travels faster than true information does. And in some ways, I think that's possibly true. And it may be psychologically the way we're built. Think for a moment about warnings. A warning is something to keep you from being harmed. And so we pay attention to warnings. And warnings usually are a bad thing is going to happen if you don't take a certain action. So, a bear shows up and, we've been trained by evolution to run the other way. Rather than standing there trying to figure out what species the bear is and how many other bears there are in that bear's family. So this idea of warnings and negative information is often the core of misinformation and disinformation intended to invoke certain actions or certain adoption of certain opinions. So we need to understand that. We need to understand our own psyches, and we need to resist, if we can, this kind of practice. And the last bullet here on digital literacy simply expands on that notion and says that as the internet becomes more penetrant, it's well past 50% of the world's population having access to it, we need to become more literate about how it works and how it can be potentially hazardous for the same reason that we teach kids to look both ways before they cross the street. So these are all things that occupy my thinking a lot. There's more unfinished business here. And again, I want to be thoughtful of time. These are huge topics, and they are in debate at this point in many different venues, especially in various of the United Nations organizations, whether it's the Internet Governance Forum or the various OECD discussions. The Secretary General himself initiated a digital cooperation effort and a panel to try to articulate that. I had the good fortune to sit on that panel. The questions that came up were, how can we cooperate across international boundaries in order to help law enforcement track down people who are causing harm? And you can see the problem. The internet was designed to be insensitive to crossing international boundaries. The little internet packets don't know when they've crossed from the United States into Mexico or Canada or whatever example you would like. So, and it was designed that way. The problem is that someone in one country can do harm to someone in another country. And so now we need cooperation to track down the perpetrators, and that means that law enforcement has to have the ability to share information under appropriate terms and conditions. They have to be able to assist each other, again, under appropriate terms and conditions. So we're looking for practices and policies that will allow cooperating countries to help make their respective populations safer in this online environment. Why are we unsafe? Well, setting aside bad human behavior, we also have a problem with software. I'm sorry to report to you that computers have been around and programmable for about, I guess, on the order of 80 years or so. And in that 80-year period, none of us have figured out how to write software that has no bugs in it. And so bugs are simply mistakes that programmers make, and often they're very simple, stupid mistakes. And I don't know if you've had experience writing software, but I used to make a living writing it, and I think I have a little dent in my forehead from the many times when I've said, "Oh, that was so stupid," because of a mistake I made in the software, which led to consequences. So figuring out how to improve our ability to avoid making mistakes in software, or at least find them before we release the software into use, is very important. And you can think of all kinds of examples where failure in the software could be pretty disastrous, like a self-driving car that runs into things. But even something simple, like a light switch that doesn't work very well because of a bug, or a webcam that somebody has been able to take over and invade your privacy, are all equally troubling. And that leads me to the last point on this slide, which is that if you are in the business of making software that is used by others, that is relied upon by others, I think you should feel a great burden of ethical responsibility to make sure that the software is as bug-free as possible, and to make sure that if in fact software gets distributed, that there is a way to fix the bugs. Which means that these devices, these IoT devices, when they're online, need to be able to download new software to correct for failures or to add new functionality. But it's very important to make sure that the receiving device knows it came from a valid source and it hasn't been changed on its path from the source to destination. Digital signatures are your friend here for integrity and for identifying the sources of these updates. So these are all practices that I think should become part of our normal pattern, and something which we should be teaching programmers in school. Well, let's go on to the next point here. I'm sure many of you are well aware that the internet isn't everywhere. And as the chief internet evangelist at Google, part of my job is to try to help get the internet into operation where it isn't right now. And there are lots of reasons why internet is not 100% accessible around the world. One of them is there may not be core infrastructure available, telecommunications circuits or radio capabilities, radio towers. A lot of infrastructure is needed to make the internet work. There may be economic barriers where it may be available but too expensive for some people, in which case they can't use it because they can't afford it. Or it may be too expensive to build the infrastructure in, let's say, mountainous regions or in rural parts of countries where there's a low population density and very expensive to pull fiber. There are lots of potential economic barriers. There may be policy inhibitors where the government doesn't permit competition or it doesn't incite competition, so you don't get people driving cost out in order to compete with each other and to give choice to the users. So policy can make a big difference in terms of internet propagation. And finally, there may be some, we'll call them educational deficits. In order to build and operate internet, you have to have certain skills and knowledge. And if that isn't available in some particular area, then it's not clear how that system will be up and made, could be created and put into operation and sustained unless there are people there who are capable of doing that. So these are all things that contribute to the digital divide, and one of my interests is finding a way to bridge that gap. This was a surprise for me, just in terms of physical infrastructure. This is a picture of the major submarine cables that are used to support internet and other communications around the world. And I must tell you that the rate at which undersea cable has been going into this architecture is just at an incredible pace. There are islands in the middle of the Pacific that are now being fiberized. It doesn't mean that everything is going to be connected by fiber, but I will say that this has been an astonishing growth of capacity, especially between major continents like Europe and the US and the like. So you can anticipate that there will be an increasing amount of high-speed linkage around the world, connecting various parts of the internet together using optical fiber. And then I don't have a slide for this, but at least I don't think so. No, I don't. So let me just mention that another thing that's happening right now is a massive investment in low Earth orbiting satellites. So if you think about Elon Musk and his Starlink system, and there are other competitors as well, Cooper, for example, and One World or OneNet. These are all investments in low Earth orbiting satellites. And to use the Starlink example, which has about 1,000 satellites in orbit, it's anticipating 42,000 satellites. At some point, if Musk is successful at this, it will be impossible to avoid access to the internet because the satellites will give full global coverage at very high speed. Some of these have been tested in the hundreds of megabits a second to ground stations on the surface. So connectivity to the internet is rapidly increasing. And I haven't even mentioned 5G, which is the successor to 4G, 3G, 2G. And that is the high-speed radio-based connectivity, which is also starting to proliferate around the world. I just thought that you'd appreciate this is wisdom from Washington, D.C., where I've lived in the last 45 years. Friends come and go and enemies accumulate. I'm sure that's an adage that some of you can relate to. I've already mentioned the Internet of Things, and this is just illustrative of some of the products that have Internet capability. The one that I thought was the most unusual is the guy that put a laptop in his surfboard and goes out on the water and put a Wi-Fi service in the rescue shack on the beach. And he goes out on the water and he can surf the Internet while he's waiting for the next wave, and I thought that was pretty creative. There are lots of others here, but in the interest of time, I'm going to keep going. This is it. Oh, I do have to tell you, these are all kinds of examples of ways in which we might use the internet and the Internet of Things. But the part I like the most is imagine having RFID chips in your clothing. So if you lose your sock, you could send a pulse around the house saying, where are my socks? And the RFID chip in the sock reports back, I'm under the sofa in the living room. So we've solved the problem of the missing sock, which I consider to be a huge contribution to humanity. You can just imagine what some of these other things are like. Bathroom scales that are internet enabled, and they send your weight to the doctor after you weigh in the morning, and then the same information gets to the refrigerator and it refuses to open because it knows you're on a diet. The future may not be as rosy as we would like. I want to shift gears now and spend just a few minutes on the interplanetary extension of the internet. This is not science fiction. This is a real engineering project. Some of you may remember that in 1997, the Pathfinder robot landed on Mars. And it was the first successful landing in about 20 years because the previous successful landing was in 1976. The two Viking spacecraft that sent by the United States landed successfully on Mars. And then after that, for 20 years, nothing worked. So when the Pathfinder landed, I got together with a team at the Jet Propulsion Laboratory in Pasadena, California. And we asked ourselves, what should we be doing then, that is to say in 1998, which will help us prepare for what we will need 25 years from now. And our conclusion was that we needed to start designing a backbone network to support manned and robotic space exploration, which would be needed 25 years hence. And of course, 25 years after 1998 is 2023, which is literally just around the corner. Well, as it happens, we started working on this design, and we tried to use TCP/IP. We thought, well, it works on Earth, so it ought to work on Mars. And we quickly discovered that even if it did work on Mars, that in between the planets, the distances are literally astronomical, and that the speed of light is too slow. So between Earth and Mars, when we're closest together in our orbits, that's about 35 million miles. And it takes 3.5 minutes at the speed of light, and of course 7 minutes round trip time. Worse, when we're farthest apart in our orbits, it's about 235 million miles. It takes 20 minutes at the speed of light to go one way and another 20 minutes to come back. 40-minute round trip time. I guarantee you the TCP/IP protocols were not designed with a 40-minute round trip time in mind. So then there's another problem. The planets are rotating, and we don't know how to stop that. So if you're trying to talk to something on the surface of a planet and it rotates out of the way, you have to wait until it comes back around again. Same problem with some of the possible orbiting satellites. So we now have a variably delayed and disrupted environment to deal with. And we ended up designing a brand new suite of protocols that we call the bundle protocols to implement an interplanetary backbone network. When Spirit and Opportunity landed on Mars in January of 2004, the original plan was to transmit data from the surface of Mars directly back to Earth to what's called the Deep Space Network. That's a network of 3 70-meter dishes in Goldstone, California, Canberra, Australia, and Madrid, Spain. The data rate that was intended for the Spirit and Opportunity rovers was 28.5 kilobits a second. And of course, the scientists were grumpy about that. Then they discovered when they turned the radios on that they were overheating, so they had to back off on the duty cycle. The result was more grumpy scientists until somebody noticed that, or reminded us that we had an X-band radio on the rovers on the surface of Mars, and the orbiters, which had been sent 2 years before in order to map the surface of Mars to figure out where the rovers were going to go, actually had X-band radios on board, and of course operating software and computing and the like, and power. So we said, why don't we use the store and forward interplanetary protocols, which we had been working on, to build a relay system, store and forward relay system, to bring the data back. And by good fortune, because the orbiters and the rovers were not very far apart, the data rate was 128 kilobits a second. And because the orbiters were outside of the Mars atmosphere, which is thin, but still present, 2% of Earth atmosphere, and had larger solar panels, it had more power. And so we could transmit data back from the orbiters at 128 kilobits a second. So we got 4 times as much bandwidth by using store and forward techniques. That is how all the data has been relayed back to Mars since 2004. All the subsequent landers, the lander on the North Pole, the 2 sets of rovers, the science laboratory, the most recent Perseverance, all of them are using this store and forward relay system. Well, we have been evolving the interplanetary protocols since that time. We now have standardized those protocols with the Consultative Committee on Space Data Systems, which is a UN agency made up of all the spacefaring nations. So they are now in a position to use those new protocols. We have them operating on the International Space Station. We anticipate that they'll be in use for the Artemis mission, which is the return to the moon that the US is initiating. We have collaborative work going on with the Japanese Space Agency, JAXA, with the Korean Space Agency, CARI, with the European Space Agency, to implement these protocols. So this is not simply a speculative thing. There is serious work going on to design, build, and deploy an interplanetary backbone. And so in the long run, what we anticipate is that as spacecraft go out containing these protocols, when they finish their scientific missions, they can be repurposed as nodes of an interplanetary backbone, or we may actually send some spacecraft out deliberately as relays in the interplanetary system. And so over the course of the decades to come, we'll see this interplanetary backbone grow in scale and capacity. I'll stop there. I know we have just a few minutes for Q&A, but I'm happy to answer questions if you have them. And again, thank you very much for letting me take time to share some of these thoughts with you.
All right. Thank you so much for the insightful information, sir. So I guess the first question someone had was that the internet transcended from, let's say, being like a fascinating gadget to being like a necessity for conducting basic activities in day-to-day life. So what are your views on like the internet as such emerging into something that is a basic necessity, and how do you think we are going to take it from here? Because there are some people without the internet, and the internet is certainly like a human necessity now, right?
So let's break this into two parts. When I think of internet, of course, my initial thinking is about the basic communication system that allows any computer to talk to any other computer. Once you have that infrastructure, of course, now the question is, what do you do with it? And that's a function of what software you put into the computers. Now, that's the application space. When Tim Berners-Lee did the World Wide Web, he added a layer of protocol on top of TCP/IP called the Hypertext Transport Protocol, and that has become one of the primary platforms in which computer communication is undertaken, and lots of applications are making use of it. So the heart of your question is, what are the applications going to be? How will they work? And what will happen if we become increasingly dependent on them? And the honest answer is that two things will happen. One, which is very good, is that a lot of that software is very enabling. It allows us to do things that we could not normally do. Think about when you do a Google search. No human being would ever search the entire World Wide Web in any reasonable amount of time, and yet we do that with our computers, and then when you look for something, we can find the answer in 0.18 microseconds. It's something that humans could never do. What about language translation, which is not perfect, but it's certainly gotten better over time, and languages impede our ability to talk to each other. You may have more experience in that than I do, because there are 22 official languages in India, just not counting all the dialects that just add to the problem. So these enabling technologies can be enormously powerful and important. They allow us to create new businesses. They allow us to create new applications. They allow us to create new knowledge and to reveal how the universe works. But at the same time, this heavy dependency comes with a price. One price is that if the infrastructure stops working, suddenly a whole lot of other things stop working. That's true of electricity too, by the way. And if you want a metaphor, when the internet stops working, lots of things don't work. When the electrical power goes off, even more things stop working. And so we have to recognize that our dependence comes with a price. And that says that we should be thinking in terms of robustness of the system that supports all these applications. And I've already spent time on the whole problem of misinformation, disinformation, social media, rivalries, and the political and economic side effects of weaknesses in the internet environment. Those are things we also have to come to grips with. And I believe that we should be conscious of our increasing dependency on technology and the potential for what is sometimes called cascade failures, where one thing fails and then a whole lot of other things were dependent on it and they fail too. So we need to be thinking about that as technologists in order to protect society from being so dependent on these things that when they aren't available, too many things break. So we had a very bad experience with that here in the United States during the winter in Texas, where the electrical power grid failed totally for several, at least 4 or 5 days or more, sometimes longer than that. And so many things depended on that. So those are the things that I worry about.
Right. Another question we have is that a huge majority of Bitsians are going to end up as engineers, and most of them are also going to end up as innovators, as startup founders and stuff like that. As someone who began this journey into a direction of innovating at a very young age, from your high school days, if I'm not wrong, what advice would you give to the audience today who would want to become an innovator or a very good engineer in the future?
Well, several things. First of all, you should recognize that the success of the internet in part was a consequence of government willingness to fund for a long time. So the Defense Department funded the Arpanet from 1969 or 68 until 1990. That's 21 or 22 years. The National Science Foundation started investing in networking technology in 1982, and it's still investing in networking technology and research since that time. That's very close to 40 years. So you should be very thoughtful about the fact that the internet got an enormous amount of government support and continues to have that support for the research side of it. On the other side, of course, it helped a lot that the venture capital companies saw eventually the value and importance of companies that either provided the service or built on top of the service. And so persistent investment in venture capital was very, very helpful and continues to be. I think it's very important for entrepreneurs to recognize that it is easy to get distracted. Sometimes it's called insurmountable opportunities, where you see so many things that you could possibly do that you don't spend enough time getting any one thing done, and then you may dissipate all of your capital and then run out. So staying very, very focused. The most important thing to keep in mind if you're starting a business is that businesses rely on customers. And so creating a customer a persistent customer is the key to a successful business. If you don't have any customers, you don't have a business. So pay attention to the service that you're providing or the product that you're providing to that customer. In the IoT space in particular, in addition to all those concerns I expressed about open source software and bugs and so on with IoT devices, think about those devices that have a long lifetime, like kitchen appliances or the heating, air conditioning, ventilation. You should imagine that the customer is expecting you to support that for the lifetime of the product. And so you need to build that into the business model. Last point I would make on this score is that when you're designing and building a product and planning to build a business around it, one of the things you should keep in the back of your mind is, how could a competitor undermine my business by inventing something new, for example, that works better? This goes along with an old expression: if someone is going to eat your lunch, it might as well be you. And what that means is that you may have to cannibalize your own business in order to stay ahead of the competitors. Sometimes that's a very, very hard pill to swallow, but sometimes it's very important.
All right. I think the last question we're going to take is that since you've been an innovator almost in the entirety of your life, and you've worked on various projects and solved many problems which made a reasonable impact on humanity per se. What is the hardest problem that you've solved till date, and why do you think that particular problem was the hardest?
Well, I won't necessarily argue I've solved it, but I think there is evidence that I have found some solutions, and I'll tell you what it is. If you're an engineer and you have an idea and you want this to be a big success, the first thing you have to learn is that you probably can't do it all by yourself. You're going to need help to do anything big. Well, how do you get help? Well, you have to sell people on the idea that they want to do what you want to do. And so the most important thing a good engineer can do is to sell other people on the idea that they want to help. This is a very important lesson. And, I have engineers sometimes who come and say, oh, those salespeople, they have all this rah stuff. And, I don't think it's very important. I want to stay focused on this technology problem, which is really hard. And I have to remind them, if the salespeople are not successful, the engineers won't get paid. And so I have huge respect for salespeople who figure out what is the customer's problem, and do I have a solution for it? And can I convince the customer that they want that solution and not my competitor's solution? So don't look down on sales. It's the lifeblood of a company. And you should help your salespeople succeed by helping them deliver products and services that customers can rely on and want to use.
All right. I think that's all the time we have for today. It was a pleasure hosting you and a delight listening to you, and we had a laugh listening on occasionally. With this, we come to the end of the Think Again series for Apogee 2021. We hope you had as much fun as we did while hosting the event. Thank you.
I had a great time. Thanks for inviting me.